Today, we are going to build a powerful framework for turning uncertainty into precise, actionable intelligence. We're moving from chaotic guesswork to strategic clarity, using one of the most powerful tools out there, experimental design.
So let me ask you this. In whatever you're working on, what really drives your results? In any complex system, a marketing campaign, a manufacturing process, a product launch, there are a million variables floating around. But which ones truly move the needle? And which ones are just noise? Or worse, a coincidence you're mistaking for a cause? Without a structured approach, we're all just making educated guesses, totally lost in the fog. But there is a disciplined, strategic framework that is designed to cut right through it all and find the truth. And that is design of experiments, or DOE.
So here's how we're going to break it down. First, we'll cover the core building blocks. Then we'll get into the strategic choices you have to make in your design. After that, we'll talk about controlling for all that hidden noise. And finally, how to decode the complex interactions in your results. A complete structured breakdown. Let's get into it.
All right, first things first, we have to deconstruct the anatomy of an experiment. Because look, to master any system, you have to understand its fundamental components.
So the most basic unit of all is the factor. Just think of a factor as any potential driver of your outcome. If you're baking a cake, right? The factors are everything that could possibly change how it turns out. The ingredients, yeah, but also the oven temperature, the baking time, even the brand of flour you use. And right away, we make our first strategic cut. We divide all those factors into two clean categories. On one side, you've got treatment factors. These are the levers you are intentionally pulling, the things you're changing on purpose to see what happens. But on the other side, you've got nuisance factors. These are the things you might not care about, like the humidity in the kitchen. But you have to account for them because they can secretly corrupt your results.
We can break this down even further. Our treatment factors, the things we control, can be split again. They can be quantitative, which is anything you can measure with a number, like oven temperature, or they can be qualitative. These are distinct categories, not numbers. Think using all-purpose flour versus whole wheat flour.
So if a factor is the question you're asking, like what temperature should the oven be, then the level is the specific answer you're going to test. It's the setting, the value, the choice you make for that factor inside your experiment. So for our quantitative factor, oven temperature, the levels we're testing might be 350 and 400 degrees. And for our qualitative factor, flour type, the levels are all-purpose and whole wheat. Simple as that. But here's why this matters, and this is absolutely crucial. Defining your factors and levels with precision is the foundation of your entire strategy. It dictates the questions you can ask and the answers you can possibly get. If you get this part wrong, the whole experiment is basically useless. Okay, so we've got our building blocks. Now we face a major strategic decision. How are we going to combine all those factors and levels into a series of actual tests? This brings us to a big choice: full versus fractional designs. And this table really lays out the fundamental trade-off. A full factorial design is the exhaustive approach. You test every single possible combination. It gives you this complete, high-definition picture of what's going on, but the cost and time can explode. The fractional factorial, on the other hand, is the pragmatic, efficient alternative. It intelligently picks a smaller subset of tests to run, giving you the most critical insights for, well, a fraction of the resources. It's kind of like the difference between having a perfect detailed map of an entire country versus just getting the most efficient route to your destination. See, a fractional design makes a really smart bet. It assumes that the most important answers usually come from the main factors, not from some super complex four-way interaction between variables. So it intentionally bundles some of those more complex effects together to save time and money. And really, this is a business decision, right? Are you on a mission to find a needle in a haystack with a full factorial, or are you pretty confident the answer lies with the main drivers? Your choice here depends entirely on your budget, your timeline, and whether you need that perfect picture or just a clear, actionable one. Now we get to something that is absolutely critical: integrity. An experiment, I don't care how cleverly it's designed, is worthless if you can't trust the results. So this section is all about building a fortress around your experiment to protect it from all the hidden noise and bias that can just make your data meaningless. And in our quality control toolkit, there are 3 core techniques. I want you to think of these as the absolute pillars of experimental integrity: randomization, blocking, and replication. Let's break them down one by one. Randomization is your #1 defense against the things you don't even know exist. So imagine a machine part is slowly wearing down over the day. If you run all of your A tests in the morning and all of your B tests in the afternoon, well, your results are going to be biased by that tool wear, right?
By randomizing the order, you make sure that any of those hidden, time-based gremlins are spread evenly across all your trials. You're basically turning a systematic error into random noise, which is so much easier to manage.
Blocking is what you do when you know about a nuisance factor and you want to completely neutralize it. So let's say you have to get raw materials from 2 different suppliers. You know this might affect your results, but it's not what you're trying to study. So you create blocks. You run a complete, randomized mini-experiment using only supplier A's stuff, and then you do it all over again using only supplier B's stuff. This totally isolates the supplier effect so it can't contaminate your main analysis. And finally, we have replication. Now, this isn't just about running more tests. It's about running the exact same combination of factor levels multiple times. The goal here isn't to find anything new. It's to measure your system's natural inherent wobble. It tells you the size of the random noise, so when you see an effect, you can be confident that it's real and not just some random fluke.
So, we've designed the experiment, we've protected it from noise. Now comes the payoff, making sense of the data. This is where we move beyond simple one cause, one effect thinking and start to decode the complex, fascinating ways that factors work together.
Honestly, the most powerful insight you can get from a designed experiment is often the interaction. This is when the whole is totally different than the sum of its parts. Let's go back to our cake. Maybe more sugar makes the cake sweeter, and a higher temperature makes it browner. Okay, simple enough. But an interaction is when high sugar and high temperature together don't just make it sweeter and browner, they create this perfect, delicious caramelization, an outcome that neither factor could ever achieve on its own. The effect of one factor literally depends on the level of the other. But there's a danger here, especially in those efficient fractional designs we talked about. It's called confounding. This is when the effect of one factor gets all tangled up with the effects of another, and your data just can't tell them apart. So, did sales go up because of the new ad, or was it the price discount you ran at the exact same time? If you can't separate those effects, they are confounded. And this is exactly why a well-thought-out design is so critical to making sure your conclusions are actually sound. Okay, let's do a quick knowledge check on a core concept, just to make sure it's crystal clear. The controlled variable whose influence we're studying, what do we call that? The answer, of course, is D, factor. Remember, the level is just a specific setting of that factor. It's a simple distinction, but man, it is a crucial one for doing clear analysis.
All right, now for a tougher one. When you're looking at your data, how do you actually spot a strong interaction? What's its visual signature? The key, the absolute telltale sign, is to look for lines that are not parallel. If you're looking at a plot and the lines are parallel, it means the factors are acting independently. But when you see them cross or spread far apart like a fan, that's it. That's the visual proof of an interaction. It means the effect of one factor is completely different depending on what the other factor is doing. That is the interaction, right there in action.
So there you have it. We've built the entire framework, from the basic building blocks all the way to design strategies and the keys to interpretation. So the only question left is this. Now that you have the tools to go from chaos to clarity, what hidden factors and complex interactions are secretly driving the results in your world, just waiting for you to find them?